Welcome to the lecture 4 on current mirror. Current mirror is a circuit which produces an image of a current, that is of a reference current. For example, there is a given current to you in one of the branch in a circuit, and you need to copy the same current into the another branch into the circuit. Where do we need these current mirrors? We have already studied that most devices operating in saturation can act as a current source. So single stage amplifiers, differential amplifiers are basically the applications of current sources. In these circuits, current sources act as large resistor without consuming excessive voltage headroom. From earlier study, we can say that output resistance, capacitance, and voltage headroom of a current source trade with the magnitude of the output current. In addition to these issues, there are several other aspects of current sources that are very important. For example, supply, process, temperature dependence, output noise current, and matching with the other current sources. So figure A shows the amplifier which is using current source. Then the figure B shows the another configuration, kind of a differential configuration in which ISS is the current source. Now how should a MOSFET be biased so as to operate as a stable current source? Now assume that M1 transistor shown in this figure is in saturation. Then from this figure you can write that I out is approximately equal to 1 by 2 mu n C naught x W by L times VGS. So here VGS is the drop across R2 and R1 and R2 is the potential divider network. Therefore VGS we get as R2 upon R1 plus R2 times VDD, and here minus VTH whole square. This expression reveals various dependencies of I out upon the supply, process, and temperature. The overdrive voltage, that is VGS minus VTH, which is here R2 upon R1 plus R2 VDD minus VTH, is a function of VDD and VTH. The threshold voltage may vary by 100 millivolts from wafer to wafer. Further, both mobility mu n and threshold voltage VTH exhibit the temperature dependence. Hence, we can say that I out shown by this expression is poorly defined. The issue becomes more severe as the device is biased with a smaller overdrive voltage, for example, to consume the less headroom. It is also important to note that process and temperature dependencies exist even if gate voltage is not a function of the supply voltage. In other words, if the gate to source voltage VGS of a MOSFET is precisely defined, then also its drain current is not. For this reason, we must seek the other methods of biasing the MOS current sources. The design of current sources in analog circuits is based on copying currents from a reference with the assumption that one precisely defined current source is already available. The study about this precisely defined source we will carry out in the next lecture. This concept is illustrated in this figure. That is, there is a reference generator I reference, which is a golden source, which is a reference source, which is already available source, and we need to copy this current into another branches into the circuit. For example, here shown I1 and I2. So now the next question arises, how do we generate copies of a reference current source? How do we guarantee that I out is equal to I reference? So consider the basic concept. So for a MOSFET, if drain current ID is function of VGS, then I can write VGS is nothing but inverse function of ID. That is, if a transistor is biased at a reference current I reference, then it will produce VGS, which is inverse function of I reference. So for example, that is shown in this figure, that there is a copy circuit and it is biased with a reference current I reference, and it is going to produce VGS over here for this transistor, and this VGS will produce I out. Or it is also illustrated in the bottom figure, that is, there is a golden reference source I reference. So this generates VGS of transistor M1, which is equal to F inverse of I reference. Now I apply this F inverse of I reference to another transistor. So it becomes VGS of M2. So obviously this VGS of M2 is going to generate I out. This structure, which is shown in figure B, consisting of M1 and M2 transistors, is called as current mirror. Here please note that we have assumed lambda is equal to 0 and the transistors are operating in saturation region. So in general case, these devices M1 and M2 need not be identical. So neglecting channel length modulation, we can write the current equations. So I reference is equal to 1 by 2 mu n C naught x W by L of 1 into VGS minus VTS square, and I out is equal to 1 by 2 mu n C naught x W by L of 2 VGS minus VTS square. VGS is same for M1 as well as M2. Now assuming that mu n C naught x is same for both the transistors and VTH is also same for both the transistors, so we get I out is equal to W by L of 2 by W by L of 1 into reference current. So this is one of the important equation. The key property of this topology is that it allows precise copying of the current with no dependence on process and the temperature, because in this equation there is an I out which is equal to, it is simply the ratio of W by L of 2 by W by L of 1 into your reference current. Thus we can say that this is a topology which allows precise copying of the current with no dependence on process and temperature. So the question over here is, find the drain current of M4 if all transistors are in saturation. And next is it possible to achieve the current amplification, say by a factor of 25? And if you say yes, how it is possible? So we have ID2, that is drain current of M2, is equal to I reference time W by L of 2 by W by L of 1. Also drain current of 2 and drain current of 3 are same, that is ID2 is equal to ID3, and ID4, drain current of 4, will be equal to ID3 times W by L of 4 upon W by L of 3. That means I can write ID4 as W by L of 2 by W by L of 1 into W by L of 4 by W by L of 3 into reference current. So that is the answer for the first part of the question. Now it has been asked, is it possible to achieve the current amplification, say by factor of 25? So the answer is yes. We have to make W by L of 2 by W by L of 1, let us say 5, and W by L of 4 to the W by L of 3, again 5. So 5 into 5, 25. Thus answer is W by L of 2 should be 5 times W by L of 1, and W by L of 4 should be 5 times W by L of 3. Now the next question is, neglecting channel length modulation, find the W by L for M1, M2 and M3 transistors. So here 30 by 2 is the W by L given for the first transistor, and the reference current is 20 microamperes. So in second transistor, the current is 60 microamperes. So from our formula that we have derived, I out is equal to W by L of 2 by W by L of 1 into I reference. So we can say here that I reference is 20 and I out expected is 60. W by L of 1 is 30. So what is W by L of 2? So W by L of 2 will be 90 by 2, because I out is 3 times I reference. So W by L of 2 will be 3 times W by L of 1, that is 90 by 2. In third transistor, that is M2 transistor, output is 200 microamperes, so it is 10 times I reference. So W by L of 2 will be 10 times W by L of 1, that is 300 by 2 is the answer. And in last case, it is 10 microamperes, so that means it is I reference by 2. Therefore, W by L of 3 will be half of W by L of the first transistor, that means it will be 15 by 2. So the answer is W by L of M1 is 90 by 2, W by L of M2 is 300 by 2, and W by L of M3 is 15 by 2. Please note that we have neglected the channel length modulation. Now the next question is how to get drain current of 0.2 IT in M5 and M6. So please observe the figure carefully. There is a reference current source, I reference. Then there is a current mirror. So drain current of this transistor to W by L of N will be I reference. Which will be equal to 0.4 times IT. And there is a transistor with 5 W by L. So obviously this IT will be 5 times I reference. Thus here ID5 is equal to 2 times I reference. IT is equal to 5 times I reference. So I reference I can say is IT by 5. So ID5, which is equal to 0.4 IT, which is equal to twice of I reference, which is equal to 2 IT by 5. So to get 0.2 IT, we can make W by L of N same for all the transistors except 5 times W by L of N. Or I must say that change this 5 W by L of N to 10 W by L of N to get 0.2 IT. Now the next question is justify that current mirrors usually employ the same length for all the transistors, or current ratioing is achieved by only scaling the width of transistors. Current mirrors usually employ the same length for all the transistors so as to minimize the errors due to side diffusion of the source and drain areas. The NMOS current sources must have the same channel lengths, because if drawn length is say doubled, then effective channel length, which is equal to drawn length minus twice of LD, is not. Furthermore, threshold voltage of short channel devices exhibits some dependencies on the channel length. Thus, current ratioing is achieved only by scaling the width of the transistors and not by the length. In our discussion of current mirrors so far, we have neglected the channel length modulation. In practice, this effect results in significant error in copying currents, especially if minimum length transistors are used so as to minimize the width and hence the output capacitance of the current source. So for the simple current mirror which we have discussed, we can write ID1 is equal to 1 by 2 mu n C naught x W by L of 1 VGS minus VTS square times 1 plus lambda times VDS1. If we consider the channel length modulation. And then similarly for ID2 is equal to 1 by 2 mu n C naught x W by L of 2 VGS minus VT square 1 plus lambda times VDS2. Now you divide ID2 by ID1. So 1 by 2 gets cancelled, mu n C naught x also gets cancelled. So there will be W by L of 2 by W by L of 1, VGS minus VTH also gets cancelled, and hence there will be 1 plus lambda VDS2 by 1 plus lambda VDS1. Please note that VDS1 is equal to VGS1 is equal to VGS2. That is, in this figure, VDS1 is equal to VGS1 is equal to VGS2. But VDS2 may not be equal to VGS2 because of the circuitry fed by M2. Now let us plot the ratio error in percentage versus the drain voltage. So ratio error means 1 plus lambda VDS2 upon 1 plus lambda VDS1 minus 1 for a typical current mirror. So for this plot, VDS1 is equal to 2 volts. Now what you can observe from this plot? There exists a significant ratio error when mirror transistors do not have the same VDS. So if VDS is changed, they don't have the same VDS. VDS is same means VDS1 is equal to VDS2. So that means it is 0 point. If there is a difference between VDS of both the transistors, then there exists a ratio error. For a given difference in VDS2 and VDS1, for example, let us say 2 volts, the ratio of the mirror current to the reference current improves as lambda becomes smaller. So that is, the ratio error for lambda is equal to 0.01 is less as compared to lambda is equal to 0.02 because output resistance becomes larger. Now let us plot the ratio error versus offset voltage for the current mirror. That means delta VT. So it is a plot of ratio error against delta VT. The conclusion from this plot is that better the current mirror performance is obtained at higher currents because VGS is higher for higher currents, and thus delta VT becomes a smaller percentage of VGS. In order to suppress the effect of channel length modulation, let us study the cascode current source. So this is the figure with the cascode current source. M1 and M2 along with I reference is a simple current mirror circuit, and we have connected M3 in cascode with M2. VB is the biasing voltage which is chosen such that Vy is equal to Vx. Then I out will precisely track the I reference IREF. Cascode device shields the bottom transistors from variations in Vp, which we have already studied in single stage cascode amplifiers. That is, there is a shielding property of a cascode device. Cascode device shields the variations, shields the bottom transistors from the variations in the Vp. So if there are variations in the node Vp, then it will not affect much the potential at Vy. So delta Vy is nearly equal to delta Vp upon Gm3 plus Gmb3 into Ro3. So this derivation comes from our single stage amplifiers. Thus Vy remains close to Vx, and hence ID2 will be nearly equal to ID1 with high accuracy. For this, L1 must be equal to L2, while L3 need not be equal to L1 and L2. Now how do we generate VB? So here our primary objective is to ensure that Vy is equal to Vx. Thus Vx must be Vb minus VGS3, or you can say that Vb must be equal to VGS3 plus Vx. So the proper dimensions if we use, then it is possible to have VGS of 0 is equal to VGS of 3. So let us modify this circuit, and the modification is shown over in this figure, center figure. So here we are connecting one more device, and gate terminal of this device is connected to VB. So finally this last figure is the cascode current mirror, wherein there is M0 transistor, M1 transistor, M2 transistor and M3 transistor. So if we choose the W by L of 3 to W by L of 0 is equal to W by L of 2 to W by L of 1, it is possible to get gate to source voltage of 0 is equal to gate to source voltage of third, so that Vx is equal to Vy. Now the question is, sketch Vx and Vy as a function of the reference current I reference. If I reference requires 0.5 volts to operate as a current source, what is its maximum value? So I have redrawn the circuit over here. We have to plot Vx and Vy as a function of the reference current. Let M2 and M3 are properly ratioed with respect to M1 and M0. Therefore, we have Vx is equal to Vy, which is equal to VGS1. So voltage at X, which is equal to voltage of Y, I can write it as square root of twice of I reference upon mu n C naught X W by L of 1 plus VTH1. This comes from our basic equation because it is in saturation region. So we know the equation for ID, and from there we can get the value of VGS. You simply rearrange the equation of ID to get the VGS, and VGS is nothing but Vx here, or you can say Vy. Therefore Vn voltage at the node n is equal to VGS0 plus VGS1. Apply KCL, so VGS1 plus VGS0 is equal to Vn. Now from this first equation we can write VGS0 as square root of 2 I reference upon mu n C naught X into square root of L by W 0 plus VTH0. Similarly, we can write VGS1 as square root of 2 reference by mu n C naught X L by W of 1 plus VTH1. So this factor square root of 2 I reference by mu n C naught X is common. You rearrange this equation. So we get VDD minus this entire term is equal to 0.5, because it is given that I reference requires 0.5 volts to operate. Therefore VDD minus, you can say, 0.5 is equal to Vn, or VDD minus Vn is equal to 0.5. So we are substituting Vn over here. Therefore I reference maximum current is equal to, you rearrange these terms, we get 1 by 2 mu n C naught X into VDD minus 0.5 minus VTH0 minus VTH1 entire square upon square root of L by W of 0 plus square root of L by W of 1 whole square. Now you can plot this Vx and Vy. So Vx and Vy will start on y-axis from VTH1 and then they will go on increasing. Now let us again consider this cascode circuitry. So for saturation region, we know that the condition is VDS should be equal to overdrive voltage, that is VGS minus VTH. In short, we can say that drain potential should be equal to gate potential minus VTH. So VD is equal to VG minus VT. So for this cascode device, just observe that VD, which is nothing but VP, so VP should be equal to Vn from this figure B minus VTH. So Vn is nothing but VGS0 plus VGS1. So we write here VGS0 plus VGS1 minus VTH. Now do the mathematical arrangement, that is minus VTH plus VTH. You will get here VGS0 minus VTH plus VGS1 minus VTH plus VTH. So in figure A, if VB is chosen low possible value to keep M3 in saturation, the I out is not equal to I reference because we need at least one VTH. So for higher accuracy in currents, we have to have minimum level of P higher by one threshold voltage. Since Vx is equal to Vy, for M2 overdrive is VDS, which is equal to VGS. Thus, it is larger by one threshold voltage. So the minimum overdrive voltage required in figure A is VGS minus VTH for M2. Then for M3 it is VGS minus VTH. So VP should be VGS minus VTH plus VGS minus VTH, that is 2 times VGS minus VTH. But if you do this, I out will not be equal to I reference because you observe from the second figure B. So second figure B tells you that I out will be equal to I reference if and only if you have the Vp, which is equal to VGS0 minus VTH plus VGS1 minus VTH plus VTH. That means it's going to consume one headroom. So cascode device or cascode mirror consumes one voltage headroom. We can modify the circuit for the low voltage operation. So the modification of the circuit is shown in this figure. For M2 transistor to be in saturation, we can adjust VB minus VTH, which is less than or equal to VGS1, that is less than or equal to Vx. And for M1 to be in saturation, VGS1 minus VTH1 should be less than or equal to VDS, that is VA, which is equal to, obviously it is VB minus VGS2. Thus from these two equations we get VB as greater than or equal to VGS2 plus VGS1 minus VTH1, and VB should be less than or equal to VGS1 plus VTH2. So VGS2 minus VTH2 should be less than or equal to VTH1. So we have to size M2 such that its overdrive voltage remains less than 1 threshold voltage. This is the modification of the cascode current mirror for low voltage operation. So the earlier circuit, that is this M1, M2 and VB along with I reference, is connected over here, and now we have connected M3 and M4 to get the I out. Now if VB is equal to VGS2 plus VGS1 minus VTH1, which is equal to VGS4 plus VGS3 minus VTH3. That means VB is equal to gate to source voltage of the second plus overdrive voltage of M1, or it is also equal to gate to source voltage of 4 plus overdrive voltage of the third. Then we can say that M3 and M4 consumes minimum headroom, and hence this is called as low voltage operation. We must still generate VB properly. So for minimum voltage headroom consumption, VA, which is equal to VGS1 minus VTH1, and VB, which is equal to VGS2 plus VGS1 minus VTH1. So this figure, the right hand side figure, depicts an example where M5 generates VGS5, which is equal to VGS2, and M6 together with RB produces VDS6, which is equal to VGS6 minus RB I1, which is nearly equal to VGS1 minus VTH1. Some inaccuracies will arise because M5 does not suffer from the body effect, whereas M2 does. Also, the magnitude of RB and I1 is not well controlled. However, this is the low voltage operation of the cascode current mirror circuits. Now let us study active current mirror circuits. Current mirrors can also be used to process the signals, that is, operate as active elements. Particularly useful in a type of mirror topology used in conjunction with differential pairs. So first of all, let us examine this first circuitry where M1 and M2 are identical. We neglect the channel length modulation. Therefore, we have I out is equal to I in. Please note the direction of I in and I out, and the circuit performs no inversion. From this small signal point of view, we can say that if I in increases by delta I, so does I out all increases by delta I. Now consider the differential amplifier where a current source in a mirror arrangement serves as a load and the output is single-ended. So the small signal gain for this circuit will be AV is equal to GM1 by R2 into twice of RO2 parallel to RO4. And if we say that output resistance of 4 RO4 is very large, then the small signal gain AV will be equal to simply as GM1 into RO2. So basically the current mirrors are used to process the signals, and they also serve as the load in the circuits, for example differential amplifiers. If you observe the earlier circuit, that is this right hand circuit, then the small signal drain current of M1 is vested. As conceptually shown in figure, this left hand side A figure, it is desirable to utilize this current with proper polarity at the output. This can be accomplished as shown in the right hand side figure B, where M3 and M4 are identical. To see how M3 enhances the gain, suppose the gate voltage of M1 increases by a small amount, increasing the drain current ID1 by delta I and decreasing ID2 by delta I. Since ID3 and hence ID4 also increase by delta I, we observe that the output voltage tends to increase through two mechanisms. The drain current of M2 drops and the drain current of M4 rises. In contrast to the earlier circuit, here M4 assists M2 with the voltage change at the output. This configuration is called as differential pair with active current mirror. An important property of this circuit is that it converts a differential input to a single-ended output. Thus here, if Vin increases, ID1 will increase and hence ID4 will increase. Therefore, ID of M2 will decrease. So to compensate for this, output voltage will increase. Now let us consider the last signal analysis for this differential configuration. If V in 1 is much more negative than V in 2, that is on this axis, it is towards left hand side, M1 transistor is off and so are the M3 and M4. Since no current can flow from VDD, both M2 and M5 will operate in the deep triode region, which carries zero current. Thus, Vout is equal to 0, which is shown in this plot. Now, as Vin approaches V in 2, that means V in 1 is equal to V in 2, so it is at this center point, M1 turns on, drawing part of the ID5 current from M3, and it turns on M4. The output voltage then depends on the difference between ID4 and ID2. So for a small difference between Vin1 and Vin2, both M2 and M3 are saturated. M2 and M4 are saturated, providing a high gain. As Vin1 becomes more positive than Vin2, ID1, ID3 and ID4 increase and ID2 decreases, eventually driving M4 into triode region. So if Vin1 minus Vin2 is sufficiently large, M2 turns off and M4 operates in the deep triode region with zero current, and hence we get output voltage is equal to VDD. Note that V in 1 should be greater than Vf plus Vth. Then M1 enters into the triode region. So in short, as Vin is greater than Vin2, ID1 increases, which will increase ID3, which will increase ID4, which decreases ID2, and therefore M1 enters into a triode region. Eventually M2 becomes off, and therefore output voltage is equal to VDD. Rest of the analysis is left for the other course. Now let us solve this numerical. Figure illustrates a reference circuit that provides an interesting reference voltage output. You have been asked to derive an expression for V reference. So this is the circuit given. Now observe this circuit. For this circuit, we can say that VGS1 plus VGS3 minus VGS4 is equal to V reference, which is available at M2 VDS. So here VGS1 plus VGS3 minus VGS4 is equal to V reference. We know that VD is nothing but VGS minus VT. That means I can say VD plus VT is equal to VGS. So I'll substitute here VGS in the form of VD and VT. So VGS1 is, I'll replace it by VD 1 plus VT. VGS3 I'll replace it by VD 3 plus VT 3, and VGS4 I'll replace it by VD 4 minus here VT4, and this entire equation is equal to V reference. Now let threshold voltage of 1 is equal to threshold voltage of 3 is equal to threshold voltage of 4. Then V reference is equal to VT plus VD 1 plus VD 3 minus VD 4. Let us say this is equation number 1. Now from figure we can say that ID1 is equal to ID3, and the transistors are in saturation, so we'll replace this ID1 by the current equation. So it is 1 by 2 mu n C naught x W by L of 1 VD 1 square, and ID3 equation is 1 by 2 mu n C naught x W by L of 3 VD 3 square. Thus from here we can say that VD 1 is equal to VD 3. So it is equation number 2. Also observe the figure. From this figure you can say that ID2 and ID4 they are same, or ID3 and ID4 they are same, correct? Therefore you can write here that 1 by 2 mu n C naught x W by L of 3 into VD set of 3 square is equal to 1 by 2 mu n C naught x W by L of 4 VD set 4 square. W by L of 3 given is 4, and W by L of 4 given is 1. Therefore you get VD set of 4 is equal to 2 times VD set of 3. Now from 1, 2 and 3 you can get V reference is equal to VT. Thus output voltage VDS, which is equal to reference voltage, is equal to threshold voltage VT. Thank you very much.